continue with our discussion on power, right? So that's what we were discussing last class. So we said there are three components to the power. One is dynamic power, two is short circuit power, right, and three is leakage power. Okay. So the idea here, at least for the first two, is the following. If I have an inverter like this, right, and the input rises with some finite rise time and then falls with some finite fall time, then the output would basically go like this. Leaving all the second order bumps that I spoke about earlier, it would look like this. And in the process, you would have a capacitor that is being charged and discharged, right? Each time the output rises and falls. Okay. So we said that when for dynamic power, we said that when the capacitor has to charge, there is an R equivalent of P which is going to charge like this, right? And of course the NMOS is cut off. Again, the assumption here is the though I showed in reality that the input has a finite rise time and fall time, here we are assuming that the input rises instantaneously or falls instantaneously, which means that the PMOS is a perfect resistor and the NMOS just cuts off, right? And therefore the charging is going to happen where all the current from the supply will be used to charge the capacitor to VDD, right? And similarly, when we are talking of the discharging case, the PMOS will be cut off and the capacitor will get discharged through the NMOS transistor like this. Right. So each time the capacitor charged to VDD, an energy of half CL VDD squared gets stored in this capacitor. Of course, the power supply has supplied CL into VDD squared. That's the amount of energy that this power supply gave. Where did the remaining energy go? It got dissipated in the resistance as heat through the PMOS transistor. Okay. So irrespective of what the resistance is or what the width of the PMOS transistor is, the same amount of energy is dissipated in that PMOS transistor always, right? And of course, when the capacitor gets discharged, right, when the output sort of falls, then the same half CL VDD squared gets dissipated through the NMOS transistor and all the current flows into the ground, right? So overall, for every charge, discharge cycle, right, energy equals what? CL into VDD square, right? Of course, this is going to be in joules because this is energy, right? Now what we are talking about is dynamic power. Okay, when we say dynamic power, it is only the power that is dissipated because of charging and discharging that load capacitor, including its own capacitance actually, right? That total capacitor, that's the power that we are referring to in dynamic power. Okay. So now the point is, if I have an arbitrary circuit like this, right, and let's say that this input is 0, okay, and then this input is switching constantly. What will happen to this input? Yeah, it will be 1, right? NAND gate output will be 1 if the input is 0. So if the other input is not switching, the output can just remain there forever. So what is the dynamic power that is dissipated by this NAND gate? It's basically 0 in steady state, right? So it's not sufficient if we just say that, okay, every cycle that gate is going to charge or discharge that capacitor. That's not true. It depends on the inputs, it depends on the input combinations, input transition combinations and everything, right? There are so many things that it depends on. And therefore, we define something known as an activity factor. How often does this node switch for a given circuit? Okay, so for example, if I have a circuit with n inputs, okay, I1, I2, IM, and outputs O1, O2 and ON, right? Now the inputs could actually be switching every time, doesn't matter, right? This could be ideal clocks, it doesn't matter to me, right? Or it could be some other arbitrary signals, okay? Now the question is, I need to find out how often every node inside this circuit is going to switch. So how do you do that? You just have to run a probabilistic simulation, feed random input combinations and allow random transitions to happen and just count the number of times that this node has actually switched. Okay, that gives you the probability of that node switching. So question is, why can't I do it for all possible combinations of the inputs? If I have m inputs, how many input combinations do I have? 2 power m. Now how many transition combinations do I have? That's much worse, right? So therefore you cannot exhaust all these things, but it's sufficient if you just take, for example, maybe 1,000,000 transitions. You just allow 1,000,000 input patterns to be applied to this circuit, and you just count what's the probability of each of those nodes switching. Now that becomes the activity factor of that particular node, right? And therefore the energy, right, average per node will become alpha CL VDD squared, depending on how often that is going to switch, right? Now if you have something like a clock, the activity factor for a clock is 1. It is switching every single cycle, right? So that is the highest possible activity factor that you can have. For every other node, it will be somewhere between 0 and 1, right? Mostly it will be actually quite low, right? So now how do we convert this to power? So what will happen is, typically these inputs here, if you look at this circuit, will get buffered through flip-flops. Okay, they have flip-flops here, flops. So what will happen is, the input actually can change only every rising edge of the clock. Even if you apply it at a faster rate, changing somewhere, right, it will not reflect in the change inside the circuit. So you can assume that all the inputs are synchronous and there is a central clock which is controlling the entire circuit, right? And if that clock is running at a frequency of f clock, right, let's assume that this clock is running at f clock, then what is the dynamic power? It's the rate of change of energy, right? You have alpha CL VDD squared, which is the average energy depending on switching factor and all that, and this is going to happen at a rate of f clock, right? Therefore alpha CL VDD squared into F clock is the dynamic power for a logic gate in general. Okay, so if I ask you what is the dynamic power of this inverter, well, the question is not complete. You have to tell me where I place this inverter, in which circuit and how, right? Then you have to tell me what its load capacitance is, right? You give me all this information, then I can say that yes, for that particular node which has a capacitance CL, it's going to have a dynamic power of alpha CL VDD squared into F, right? Clearly, VDD dependence being quadratic is the strongest way in which you can control dynamic power. If you drop VDD by half, your dynamic power will drop by 1/4, right? So this is the strongest control of dynamic power. Okay, so what you have to do is, if I am given a particular circuit like this here and I want to calculate the total dynamic power, I need to estimate first what is the switching factor of this node, what's the switching factor of this node, what's the switching factor of this node. Then I have to estimate what the total capacitance is on each of these nodes, right? Then for each of them, it's going to happen at alpha CL VDD squared into F. Okay, any questions here? So during steady state, the dynamic power is not even defined, because the capacitor is just holding charge and it is being driven to either VDD or ground, no problem. Okay, any questions on dynamic power? Okay, so let's now move to short circuit power. So we made an assumption in dynamic power that the input is going to change instantaneously, right? That means the PMOS becomes a resistance, the NMOS becomes a cutoff switch, or vice versa. NMOS is a resistance, PMOS is a switch that is cut off completely. In that model, there is no current between supply and ground at any point in time, be it in steady state or during the transition, right? Of course, in reality that's not true, and therefore we need to consider that also into our calculation here. V in, V out. So my input, as I told you, is going to go like this. Okay, V in. So let's now plot the current IVDD. Okay, there's going to be a current that's going to flow from VDD to ground like this. Obviously, in steady state, it's going to be 0, right? At what point will the IVDD become non-zero first? Yeah? When V input crosses VTN, obviously it is going to turn on the NMOS transistor. PMOS is obviously turned on already. Therefore, you will start having IVDD after V in crosses VTN. Now, at what point will it turn off? Will it come back to 0 again? Yeah, or VDD minus mod VTP, or you say VDD plus VTP. So here, so this, by the way, this for this graph, this is time. Okay, so therefore here this is these are the 2 points, VTN, VDD plus VTP, right? So now in between, your current is going to go up and then come down, right? As the input crosses VTN and starts turning on the NMOS transistor, NMOS starts in saturation, PMOS in linear. Slowly the PMOS will also come to saturation mode, at which point the current will be maximum. What is that point called? Trip point. Vin equal to Vout equal to Vm, right? After that, again the PMOS starts going into saturation, NMOS will come into linear, therefore reducing the current, and then back into cutoff. So in this region, you can approximate the current as a triangular region like this, right? And this we are going to call it as that, let me call it I naught, right? Or no, let me call it I peak, IP. Okay, this is that current that we evaluated at Vin equal to Vout equal to Vm. Now similarly in the falling edge, you are going to have exactly the same kind of thing. Somewhere out here it will happen, out here it will happen, and the current will, maybe I should remove all this, too many lines there. So this is again my VDD plus VTP. So this again will go up like this, come down to 0, and then you will be done. Okay. So now we just need to calculate the short circuit energy, right? So what is the short circuit energy? ESC. Integral VI dt, right? So let's assume that this is going to happen for a particular time t, right? So it will simply be 0 to t. What is V? Where is the current coming from? VDD. So what is the V in this equation? Integral VI dt. The current is coming from this supply. I am looking at the power delivered by the supply. So what is the V in that equation? VDD. It's a constant into I short circuit of T, right? Or I called it I VDD into dt, right? So basically it's just multiplying by VDD and finding the area under this triangle, right? So that is nothing but half VDD into I peak, right, into half base into height, right, into T. Now you can, if I give you the slope at which the input is rising, then you can calculate what this T is, how long it takes to go from VTN to VDD plus VTP, right, given the slope is say VDD by T rise. Let's assume that this slope, or it's also called slew, is VDD by T rise, and this slope is VDD by T fall. So let's assume T rise equal to T fall. So can you tell me what the answer is for the short circuit power? I mean energy. Yeah. Let's make an assumption that VTP is minus VTN, right? So you can write this as minus 2 VTN by what? VDD into T rise, right? Assume that VTN equals minus VTP. If of course this expression here is only for the rise. For a rise and fall, it's going to be twice that, right? So I can just say VDD into IP into T, IP into T, and then you substitute this expression, you will get the expression for the short circuit energy. Clear? Right? So remember that this is going to happen for a very short period. Okay? Of course, it doesn't happen in steady state, but in the transition period, even this thing is going to happen for a very short period. Okay? So maybe if your slew is very bad, then the amount of time at which the current can flow is going to be large, right? But usually in high speed circuits, you will ensure that the slew is also very good, and therefore it's a extremely short period. Clear? So therefore you can write ESC as, can someone tell me the expression? VDD into IP into VDD twice VDD minus 2 VTN into T rise, correct? No, I thought we removed the half because this is for rise and fall. See, this was basically the half BH of here, right, in this region. What about this region? So when it rises and falls, the charge discharge cycle is what I am asking for. See, T is because what I am saying is it's going from 0 to IP in a time of T, right? So, oh yeah, you're right, sorry, you're right. This is not T by 2, correct. So it's the input is taking a time T to go up. Yeah, you're right, sorry, that's a mistake. So this will vanish. Okay, is that fine? Huh? Oh, VDD will get cancelled. VI into T, correct, yeah. Power into time is energy, yeah. Okay. Now again, just like dynamic power, this is a transient phenomenon. Only when the input is making a change will this happen, and therefore the same things that we discussed there will apply here also. You need the activity factor, only when that switches is going to happen, and so on. Therefore the short circuit power is going to be alpha ESC into F clock. Okay, so alpha into IP into T rise into F clock. Why? No, yeah, but as she pointed out, see, I am giving you that the input rise slope is VDD by T rise, correct? So it takes, the input takes from 0 to T, to go from VTN to VDD plus VTP. So you have to look at this guy. This is T. If you look at this triangle, this is T. Okay, and that is the slew. That's what I'm defining as the slew. Clear? Yeah. So therefore, that's, yeah. Okay.